Well, heidi-ho, everybody, and welcome back. This is Unit 4, Lesson 9. In case you were wondering, we do not have a Unit 4, Lesson 8. I decided to take Day 8 for Unit 4 and give my classes some classwork to practice more log functions, okay? And we are going to be using some more log functions today as well. And they will become really helpful in solving for a variable which is in the exponent when we can't get the same base. Same base was easy. But when you can't get the same base, I'm going to give you a little hint here. It's still easy when we use log. Okay? So let's get started. Okay, solving an exponential equation using common base. All right. I'm looking at this right now, and I see that 16 and 8 can both be written as a base 2. 8 is 2 cubed, and 16 is 2 to the 4th. Yep, that's 24. 2 to the 4th, better. My one thing that I cannot forget is this 16 here has an exponent of 3x. So this 16, 2 to the 4th is 16, also needs a 3x. Now, I cannot forget my exponent rules. Exponents raised to exponents need to be multiplied together. So I've got 2 to the 12x equals 2 cubed. All right, if the bases are the same, the exponents must be the same. So 12x equals 3. And if I divide both sides by 12, I get x equals 1/4. Okay? Simple enough. Yes, we can get fractions as answers. It's fine. You're good. But what if I wrote it as 0.25 because that's a decimal? That's good. But why would you go through calculating that when 3 over 12 reduces to 1/4? I don't know. Either way, that's just me. You're good to go. So now we come to this problem. I'm going to solve this exponential equation, but I can't get them with common bases. All right, let me move this up here. I cannot, for the life of me, all right, say, well, I can represent both 18 and 5 with a common base. I cannot. So what do? This is where we need to use, okay, if we can't get a common base, we use log or natural log. I'm going to use natural log because it's 2 letters. It saves me writing a letter. I don't know. And when we start to get into upper level math, the number e is important, and we need to use natural log for that. So I'm just in the habit of using natural log. Okay? You can use log, and you should get the same answer. I will show you in a moment. But what is the importance behind log and natural log? We had one rule. Okay, and I believe it was Unit 4, Lesson 7. That said, if I have something with an exponent, and I take the log or the natural log of it, okay, that means I can bring my exponent down. Okay, whether it's log or natural log. All right, so same thing. If I took the natural log of something, the exponent comes down. And that's going to be super, super helpful, especially if our exponent is a variable and we want to solve for it, like it is for problem number 1. Let's take a look at that right now. Okay. I cannot, for the life of me, again, find a common base. So what I'm going to do is I'm just going to take the natural log of both sides. I'm going to take the natural log of 5x and the natural log of 18. Because I do that, my exponent, I'll do this in green, my exponent can now come down. All right? So let's rewrite that. My x comes down times the ln of 5 equals the ln of 18. All right? Now keep in mind you are now multiplying x times the ln of 5. The one thing I need to do to get my x alone is divide by the natural log of 5. What I do to one side, I have to do to the other. Please, please, for the love of God, Do not say, oh, my natural logs cancel and I have 18 over 5. That is wrong. Natural log is a function. Okay? Natural log is just like the square root function. What do I mean? Okay? Natural log is like the square root function. If I have the square root of, I don't know, 25 over the square root of 4, I cannot just say, oh, my square roots cancel and I get 25 over 4. That's poo-poo. We all know that the square root of 25 is 5 and the square root of 4 is 2. Okay, 25 over 4 is not 5 over 2. Okay, this is a function, means I need to put a number in there to use it. Same thing with natural log. It is not a value. It's an operation, so to speak. I can't just put natural log and leave that alone. It needs a number in here. Okay, much like the square root, you can't leave it alone. Okay, it's an actual operation. It's a math operation that's performed to a number. So what do you do at this point? Guess what? If x equals the natural log of 18 over the natural log of 5, just put this in your calculator just like this and hit enter. It's really that simple. All right, so let's clear this out. And I will put alpha y equals enter. I always like to use this when I'm dealing with fractions. The natural log of 18 divided by the natural log of 5. And if I hit enter, I get approximately 1.79. We'll round 3 decimal places. Okay, that is approximately 1.796. All right. Now, I said it doesn't matter if you use natural log or log, meaning instead of, at this point, instead of putting natural log for both of them, I could have said the log of 5 and bring my x down equals the log of 18. I can use either natural log or log. I cannot use both. I cannot say x times the natural log of 5 equals the log of 18. You either use logs in both of them, or you either use natural logs for both of them. Okay? This is good. This is good. This is a no-no right here. Okay? I just always use natural log. Okay? So what happens if I would have used log? If I put log in place of both of my natural logs, the log of 18 divided by the log of 5, and I hit enter, I get the same exact answer. Okay, I'm going to bring this over here. You'll notice this is the same exact answer. Okay, I'll put it right there. They're both there. Okay, so I can use either logs or I can use natural logs, but I can't use both in the same equation. All right, not to solve like this. All right, pretty good. Let's practice this a little bit more. All right, and by the way, the same rules apply. Okay, I need to get my base and exponent alone, all right, and then apply the logs where possible. So let's take a look at number 2. The first thing I'm going to do is I want to get this base and exponent alone. Okay, so I want to get this alone. So I want to get rid of that 4. So I'm going to add 4 to both sides. So I've got 2 to the x equals 1,560. So you might say to yourself, well, maybe I can get 1,560 in base 2. Maybe, but even if you could use same base, you can still use log to solve it. Okay? So in other words, if I had 5x equals 25, well, I know 25 is 5 squared, right? So x has to equal 2. I can use same base. But I can also use natural log in this instance. I can use natural log, bring my x down, of 5 equals natural log of 25. And if I divide both sides by natural log of 5, this still ends up being 2. Okay, so I can use log and natural log for situations where, I could get a same base. It would take some students a long time to find out if this was a base 2. Instead of using all that time to figure that out, why don't you just use natural log? You know it's going to work. So let's just do that. Okay? I'm going to take the natural log of both sides. My x is going to come down. So I've got x times the natural log of 2 equals the natural log of 1560. Right? I'm going to divide both sides by the natural log of 2. Divide this by the natural log of 2. I really should put parentheses. I should get in that habit of doing that. In calculus, sometimes they don't, but it's got to be obvious. But you should get in the habit of doing that. So I'm going to put this in the calculator. Let's go. So it's 1560. I don't have to use the alpha y equals function. I just take the natural log of 1560, divide that. Ooh, my 5. Insert 5, don't forget it. Okay, and then take the natural log of 2. And my answer, if I round 3 spots, is 10.607. So that x is approximately 10.607. All right, I'm going to go quickly through the rest of these. And if you want to pause it and do them now and see if you get the same answer, now's the time to do that. All right. Number 5, I'm going to add 3 to both sides. So I've got 4 times 2 to the x equals 20. I'm going to divide by 4. And why am I doing this? Because I need to get my exponent and base alone. Okay? And now I've got 2 to the x equals 5. If I take the ln of both sides, my x comes down. It's x times the ln of 2 equals the ln of 5. I divide both sides by the ln of 2. Whoop, whoop. Yep, there they do. I'll write this up here, and I should have the ln of 5 divided by the ln of 2. 2.322. That is approximately 2.322. That 1 gets rounded up because the number after it was a 5 or bigger. 2.322. 3. Okay, same rules still apply. I already have the base and exponent alone, so I'm going to write over this, the natural log of both sides. So my exponent comes out in front. Yes, my exponent is x plus 3 times the ln of 6 equals the ln of 50. Okay, so now I'm going to still solve for x, okay, but I'm going to do this one thing at a time. I'm still going to solve for x. The first thing I got to do is I got to get rid of this ln of x, then I got to subtract 3. Okay, my order of operations still apply, okay? I'm doing reverse order because I'm solving for x. I'm peeling away. Divide by ln of 6, divide by ln of 6. So I've got x plus 3 equals ln of 50 over the ln of 6. Now I just subtract 3 from both sides. So my x is going to equal whatever this is. The x is going to equal whatever that is. And again, I'm going to use my calculator. I'll do this in one step here. It's the ln of 50 over the ln of 6. And then I pop out and I subtract 3. Negative 0.817. So that is approximately negative 0.817. Ooh, fancy. Let's do this, okay? Fractions, big deal. I'm still going to take the I have my base and exponent alone, right? So I'm still going to take the ln of both sides. My exponent comes down. I have x over 3 plus 1 times the ln of 1/2 equals the ln of 1/6. All right? Multiple steps here. I'm going to divide by the ln of 1/2. Gone. Divide by the ln of 1/2. So now I've got, and I'm writing all this out. I mean, you can start to kind of imagine what's going to happen, but let me write all this out. I've got x over 3 plus 1 equals the ln of a sixth all over the ln of a half. Okay, now I'm going to subtract 1 from this whole side. All right, so this goes bye-bye. Now I have x over 3. How do I get rid of this? I got to multiply this side by 3. What do I do to one side? I have to multiply the whole side here by 3. So x is going to approximately equal. I'm going to put this just like I see it in my calculator. Parenthesis, alpha y equals enter. It's the ln of 1 divided by 6 all over the ln of 1 divided by 2. I'm going to pop out. I'm going to subtract 1. I'm going to close that parenthesis. Then I'm going to multiply by 3. 4.755. 4.755. My, these look strange, but who cares? Do the same process. Let the calculator do the math. Just set it up. Meaning, I want to get my base and my exponent alone. I want to get rid of that 17. Let's divide by 17 both sides. So 5 raised to the x over 3 equals 4 over 17. Okay? Now, I'm going to take the natural log of both sides. So I've got my exponent that comes down. I've got x over 3 times the natural log of 5 equals the natural log of 4 over 17. All right, well, let's just solve this like I would anything else. Let's divide by the natural log of 5. Bang, boom. Divide by the natural log of 5. Now I have x over 3 equals the natural log of 4 over 17 times the natural log of 5. The last thing I need to do is I got to multiply this left side by 3, which means I got to multiply this right side by 3. So x is approximately, and I put this in the flipping calculator. All right, parentheses, alpha y equals enter. It's the ln of 4 divided by 17 all over the ln of 5. Okay, close that parenthesis, and I'm going to multiply that times 3. Negative 2.697. Okay, negative 2.697. There you go. And this last one, you're like, well, how do I use this? I don't look it. What does x equal? X equals log base 7 of 21. I'm just going to put this in the calculator. Don't get crazy. You already have x alone on one side. X equals the log base 7 of 21. So I'm going to hit alpha, window, and I'm going to pick choice 5 where it says log base 7 of 21. I'm going to hit enter. Get 1.565. So x is approximately 1.565. That was a gimme. You know, I don't say anything to students, and I let them try number 7, and they start doing log on both sides. They start getting crazy. They mahoganize it, then realize they got to re-log it. It just, leave it like it is. It's done for you. All right. All right, this is where natural log really comes into play and really becomes helpful because we have the number e here. Let us not forget that the natural log of e equals 1. How come? Because the exponent to this e is 1. These cancel. So the natural log of e to anything ends up just being whatever the exponent is. All right? In this case, it was a 1. In this case, it was an x. So what we're going to do is we're still going to peel everything away except the base and the exponent. We want the base and the exponent for 1. Look at here. want the base and the exponents, okay, for number 3. And we are going to, solve these using natural log. Now here, you can use log, but whenever there's an e, use natural log, okay? There's never a case where you have to use log, okay? But there is a case where, I suppose you don't have to, but it is substantially easier to use natural log. That's why I just always use natural log, okay? So let's do problem 1. Let's subtract the 2 first. And I get 4e to the 2x equals 14. Okay, now I'm going to divide by 4. So I've got e to the 2x equals, that reduces, but you know what? Leave it like this and let's let the calculator do all the work. All right? Now, I'm going to take the natural log of both sides. Here is where it gets easy. These cancel, okay? I've got 2x equals the natural log of 14 over 4. All I got to do is divide by 2 now. You see how natural log and e work? It becomes really, really easy. Now I've just got to put this in my calculator and hit enter, and that's what x is equal to. And we're going to do that right now. So I've got the natural log of 14 divided by 4. And I'm going to take that and divide it by 2. And you should get 0.626. Okay, and just for poops and giggles, let me use the fraction function and make sure I didn't have to put parentheses around that top ln. I shouldn't have, but 14 divided by 4, all divided by 2. 0.626. Okay, same deal. That's why I always, by default, use that fraction function, because that line in the middle of your fraction will automatically separate your numerator and denominator. You don't need to use parentheses. So you have 0.626. Let's take a look at the next one. All right, easy. Let's divide by 2. And I've got e to the negative x equals 10. All right, well, I know natural log and e cancel. Negative x equals the natural log of 10. Well, all I got to do is negate both sides. If I flip the sign over here from negative to positive, I got to flip the sign over here from positive to negative. So x equals the negation of the ln of 10. The negation of the ln of 10. Negative 2.303. I love natural log. Love it. Now, if you feel comfortable enough, why don't you try number 2? Because I'm about to do this right now. About to wreck this thing. Let's go. All right. If you want to pause it, do it, and check to see if you're right. Subtract 7 first. Negative 2e to the x over 2 equals negative 6. All right. Let's divide by negative 2. Bye-bye. So I've got e to the x over 2 equals, that's a positive 3. I take the natural log of both sides because I can. This goes bye-bye, and I have x over 2 equals natural log of 3. And the last thing I need to do to get x alone is I multiply the left side by 2, and I got to multiply the right side by 2. So in my calculator, x, I just enter this, and that's what x should equal. That is approximately 2 times the ln of 3. Oh, beautiful. 2.197. So we'll go back here, and we'll say 2.197. Love it. Love it. I love natural log. Love it. Okay, let's look at some applications, something that might be on a final, okay, for exponentials. Not all of them deal with e. That's fine. But they're all exponentials. They all have a variable in the exponent. So one says that for each of the following here, Which of the exponential functions below show growth and which show decay? For each example, identify the rate of growth. It does not say percent, so rate should be in decimal format. Okay? This is bigger than 1, so that's G for growth. How do I find if that is what the rate is? 2, that's the same thing as 1 plus my rate. So if I subtract 1 from both sides, my rate is 1.00. It grows by 1, 100%. Okay? I'm going to rip through these. If you want to pause this and do these now, go right ahead, because I'm about to do these. All right? B is decay, because it's less than 1. Okay, so that's 1 minus r equals 0.5. If I subtract 1 from both sides, my negative r should equal negative 0.5. But I want positive r, so I should make this positive. My rate of decay is 0.5. Next one, that is definitely growth, bigger than 1. And my rate of growth is 0.3, because 1 plus 0.3 is 1.3. All right, doing good. Doing good. Decay, because that is less than 1 in parentheses, my b value. And my rate of decay is 0.2, because 1 minus 0.2 gives me my 0.8. That's my rate of decay. Love it. It's already 1 plus. If I see a plus sign here, I know it's growth. And I know that my rate is 0.025, because the rate is what I add to 1. Thank you very much, mister, for doing that. And the same thing for the last one. It's going to do yellow. I don't know if you can see it so good. I'll try it. That is decay, because I am subtracting a number from 1. And the rate is what I'm subtracting, which is 0.4. Nice, good. This is good, healthy exercises. Makes the brain say, thank you, I feel jacked. And it should. I'm sorry about that. I got excited. All right, here's another good problem. Since January of 1980, the population of the city of Brownville has grown according to the mathematical model y equals 720,500 times 1.022 to the x, where x is the number of years since 1980. Okay, explain, for part A, what the numbers 720,500 and 1.022 represent in this model. Okay, well, first of all, 720,500 is your A value, right? That's your initial, it's your starting value. That's your initial population, because in our case, we're dealing with population. That's our initial population, or the population in 1980, because didn't they say this started since 1980? So that's our initial population. So what does the 1.022 represent? Well, I know it's growth, since 1.022 is bigger than 1. And I know my rate is 0.022. That's my growth rate, because that's what I added to 1. If you want to write this, 1.022 equals 1 plus 0.022. You don't have to. This is enough, and this is enough, okay? These are just explanations, okay? We answered the question. We explained. I guess when I said I need explanations, it does say explain here. So, good. If a student answered like that, I would say to myself, like, they really know what's going on. All right, B, what would the population be in 2000 if this growth continued? Now, this is good. My equation is y equals 720,500 times 1.022 to time. My time is years since 1980. 2000 is 20 years plus my 1980, right? It's 20 years since 1980. So I can't put 2000 in for my exponent. I need to put 20 in. And then I need to hit the enter key in the calculator and see what it gives me. So I'm going to clear all this mumbo jumbo out. 720,500 times 1.022 raised to the 20, because it is 20 years. And I hit enter. Oh boy. All right. Now, different teachers will tell you different things. But I would say that that answer is this. I wouldn't round up. A lot of people say round up, and I'm sure they would accept either answer. Population, okay, shouldn't go up until a child is born. This woman is roughly 75% through her pregnancy. That's what that means. Okay, so that child that's born doesn't count in the population until they're born, until they're 100% done with the population. So I would accept 1,113,401 is the population. Now, if your teacher just always expects you to round, you can put 402, and that's fine. I probably would not take a point off for that. I would accept that. But in real life, it doesn't matter how pregnant you are. It matters when the child is born, when you are done with the pregnancy. Okay? And that's just some advice from your Uncle Frank. Let's delete that. There you go. So the last one here. Use this model to predict about when the population of Brownville will first reach 1 million. Well, obviously in 2000, it was over 1 million, so it should be before the year 2000. Let's just put some common sense. If my answer came up with the year 2007, that's wrong. Okay? So let's take a look at this. My equation, 720,500 times 1.022 to the x. When will that population be 1 million? I'm going to put this in y1. I'm going to put this in y2, and I'm going to see where they intersect. That's the best way to do it. Or, if they want me to do this algebraically, they didn't say algebraically. But now that we know how to use log, let's use log. Oh, my. Oh, my. All right. First, I'm going to divide by 720,500. Bang, bang. Divide this by 720,500. So now I've got 1.022 to the x equals this fraction here. If you don't mind, for the sake of writing, I'm going to cancel off the last two zeros. You don't have to. I won't. On a test, you probably wouldn't. So I've got 1 million all over 720,500. Okay. Now I'm going to take the natural log of both sides so I can bring my exponent down. Whew, all this rewriting. So now I have x times the natural log of 1.022 equals the natural log of 1 million over 720,500. The last thing I need to do to get x alone, because I'm multiplying it, is to divide by natural log of 1.022. Bang, boom, and I divide this side by the natural log of 1.022. X would approximately be alpha y equals, enter the natural log of 1 million. 1, 2, 3, 4, 5, 6 divided by 720,500 all over the ln of 1.022. Bang. That should be less than, yep, okay, we did something wrong. We did something wrong. I forgot a 0 in this million. If you're like, Visca, you forgot a 0. I needed 6 zeros. See, I hit the key in the calculator, and it didn't show up. Or at least I thought I did. Second, insert a 0. Okay, now hit enter. Much different. 15, yeah, it shouldn't be 20. It should be 15 years. That's approximately 15 years since 1980. But they didn't want how many years since 1980. They want to know, like, when. If someone asks you when, 15 years since 1980 will be 1995. 1995. Look, it just all works. That was a good problem. That was a great problem. Last one, and you guys have been doing really well. Hang with me here. I know we're over the 30-minute mark. The half-life of medication is the amount of time for half of the drug to be eliminated from the body. The half-life of Advil, or ibuprofen, is represented by this equation here. What's remaining in the body, my initial dosage, and I multiply it times 0.5 raised to the t over 2, where r is the amount of Advil remaining, and m is the initial dosage, and t is in time in hours. Okay? A 200 milligram dosage of Advil is taken at 1 p.m. 200 milligram, that's our initial. Okay? It's taken at 1 p.m. How many milligrams of the medication will remain at 6? 1 to 6 is 5 hours. So I'm going to take 200, set it equal to, they want to know how much is remaining. I'm going to take 200 times 0.5, so my time over 2, my time is 5. If I put that in the calculator, times 0.5 raised to the 5 divided by 2, I will get 35.355. So I'll say 35.355, and that's in milligrams, okay? All of our things are in milligrams. Last one. Now it says the doctor says a person can take another 200 milligrams when there's 10 milligrams or less remaining. So I'm going to see, well, when will I have 10 milligrams in my equation? We want to know when. So I'm just going to solve this, okay, for t. I'm going to use natural log eventually because my exponent is in the variable. And I'm going to first start by dividing by 200. Boom. 10 divided by 200 equals 0.5 t over 2. Yep, that's my marker. If I take the natural log of both sides, all right, my exponent comes down. So I've got the natural log of 10 over 200 equals t over 2 times the natural log of 0.5. Okay? Now I'm going to divide both sides by the natural log of 0.5. Okay, divide both sides by the natural log of 0.5. Now I've got the natural log of 10 over 200 all over the natural log of 0.5 equals t over 2. And the last thing I need to do is multiply this side by 2. And I multiply this side by 2. So I put this whole poopy thing, which equals to t, in the calculator. I'm excited. Let's see when this guy can take more pain medicine, because that's what we need in this country, more pain meds. Alpha y equals, enter. Alpha y equals, enter. The ln of 10 divided by 200 all over the ln of 0.5. And I'm going to pop out and multiply that times 2. Ooh, my 200. See, again, that 0, that nasty 0 in the calculator. 0, then the parenthesis. Okay, 10 divided by 200, all over the ln of 0.5. Bam! 8.64 hours. That's approximately 8.64 hours. If you're a doctor, you tell someone, about 9 hours. But there you go. Fantastic. Then welcome to the wonderful world of using logs to bring variables, which are an exponent, down. See ya.